only new work. It's very incomplete work. And part of the reason that I'm talking about it here is in the hope that some of you tell me what I'm missing or what I've gotten wrong, or at least give me some ideas of where to go with this next. So the basic idea that the basic starting point of this work is fairly simple and I think is becoming more widely appreciated these days. And this has to do with the behavior of theories with gauge symmetries on manifolds with boundaries. So to start with, most of the physical theories that we know are written in terms of an action whose variation gives classical field equations and whose path integral gives quantum amplitudes. If you have an action on a manifold with boundary, typically you are forced to add an additional boundary piece to the action. In the classical theory, this boundary piece is required just by saying that you want the action to have genuine extrema. When you vary an action, you typically have integrations by parts, which you don't care about if the manifold doesn't have a boundary. But if it does, you get boundary pieces that you have to make sure get canceled off. In the quantum mechanical formulation, it is probably true, it's known to be true in simple cases, that the correct boundary term is needed in order to sew together amplitudes. That is, if you have a path integral going from here to here and a path integral going from here to here, quantum mechanically you should be able to combine those by summing over a complete set of intermediate states. In other words, by integrating over appropriate fields at the boundaries. But this only works if you have the right boundary term to your action. Now, for an action without gauge symmetries, this is all fairly straightforward and non-controversial. If you have gauge symmetries, though, things change a little bit, because typically, unless you are very careful and very lucky, the boundary term in your action is not going to be invariant under the full gauge symmetry. In other words, that means that some configurations that used to be considered physically equivalent are now inequivalent because the action, including the boundary term, is no longer fully invariant. Another way of saying this, which is essentially equivalent, is that if you want to add the boundary term and preserve gauge invariance, it may be necessary to add additional degrees of freedom that restore the gauge invariance at the boundary. So I'm going to talk about how this works for 2 plus 1 dimensional gravity. First, very briefly summarizing some old results for the asymptotically anti-de Sitter case, and then mostly talking about new work in progress for the asymptotically flat case. The reason that this is that 2 plus 1 dimensional gravity is an interesting playground for this is that in pure gravity in 3 space-time dimensions, there are no propagating degrees of freedom. So most of what's interesting happens just with this boundary term. But presumably, at least I hope, these methods can be fairly straightforwardly generalized to 3 plus 1 dimensions, where they will probably relate to recent work by people like Andy Strominger on boundary symmetries and super translations and superrotations. I'll say a little bit more about that at the end. OK, so 2 plus 1 dimensional gravity. There are 2 tactics for understanding these boundary terms. First of all, it's been known for many years now that you can rewrite 2 plus 1 dimensional gravity as a Chern-Simons gauge theory. In that formulation, there's a very simple decomposition of the fields into a gauge fixed piece and gauge transformations. And the reduction, the resulting boundary action is in principle very well understood, except for the particular boundary action that comes with quantum gravity, which is the one simple conformal field theory that's not very well understood. It's something called Liouville theory. That's life. But it is known in particular that the boundary term is the correct one for composing path integrals, for sewing integrals together at boundaries. So this is all very nice. The problem is that it doesn't generalize beyond 3 dimensions. This reduction to a Chern-Simons form is very particularly a characteristic of 3 dimensions. So instead, I'm going to dive in and do this the hard way, working with a standard metric formulation. This has the disadvantage that there isn't a simple description of the finite transformations, the diffeomorphisms, in terms of some simple gauge fixed quantities and some functions that describe the diffeomorphisms. The boundary theory might not be local because diffeomorphisms, the relevant gauge symmetries, move points around. But presumably, this method can be applied to more than 3 dimensions, and so it's worth spending some time on. So let me first briefly summarize some results for the asymptotically anti-de Sitter case. This is interesting because partly it touches on the ADS-CFT correspondence. And in fact, this is really the first place that a correspondence between bulk dynamics in anti-de Sitter space and gauge theory at the boundary was discovered and explored in any detail. It's interesting because the asymptotically anti-de Sitter case is the case that includes black holes in 2 plus 1 dimensions, so you might be able to learn something interesting about black holes. And it's interesting because it's simple, because the asymptotic behavior is well understood. So there are old results, mathematical results of Pfefferman and Graham, who show that in any asymptotically anti-de Sitter space, in this case in 3 dimensions, you can expand the metric in terms of a radial coordinate and set of an angular coordinate and time, which live in this 2-dimensional Lorentzian metric, Gij, where Gij has some standard expansion. And in fact, the Einstein field equations in this case can be solved exactly, and all of the terms in that expansion can be written down in terms of a finite number of free functions. The kind of diffeomorphism that I'm interested in is one that doesn't respect the boundary conditions. So here, the boundary conditions are placed at a fixed value of this radial coordinate rho, which eventually we take to infinity in some limiting process to get full anti-de Sitter space. And so the diffeomorphisms that intuitively you would expect would not respect those boundary conditions are diffeomorphisms that move the boundary, that is, diffeomorphisms in the radial direction. And in fact, they don't preserve the boundary action. You can write such a diffeomorphism in terms of some function phi that describes the motion of the boundary, and some higher order terms, terms of order e to the minus 2 rho, which are completely determined by just demanding that the general form of the metric remain in this Pfefferman-Graham form. The action for 2 + 1-dimensional gravity is the ordinary Einstein-Hilbert action plus a boundary term. This is the Gibbons-Hawking boundary term, the extrinsic curvature of the boundary. There is also an additional term proportional to the volume of the boundary, which is added in order to subtract off infinities in the limit that the boundary goes to infinity to leave the total action finite. The original boundary was at some value of rho, say rho bar. The new boundary is at rho bar plus this variation. So all you have to do is take this new boundary, figure out its normal vector that determines the extrinsic curvature, figure out the induced metric that determines the volume, stick them into this action, and what you see is that the action is not invariant. That is, it's not independent of phi. And instead, you get an induced action at the boundary, which depends on the scalar curvature at the boundary, and which can be recognized, if you're used to two-dimensional conformal field theory, as a limiting form of an action called the Liouville action. What do you get out of this? Well, first of all, this is a two-dimensional conformal field theory. Two-dimensional conformal field theories are characterized by a number, the central charge, which was known for 2 + 1-dimensional gravity from work of Brown and Hinault, who didn't look at conformal field theory, but just looked at the symmetries of the asymptotic symmetries of the theory. This Liouville theory has the right central charge. And it turns out that this means that you can use standard conformal theory techniques to calculate the density of states and therefore the entropy. And if you are looking at a configuration that contains a black hole, you determine the entropy this way, you get the right answer. You get a quarter of the horizon area, in this case, the horizon circumference in Planck units. You can do more than this. You can take this conformal field theory and couple it with matter ad infinity in the conformal field theory, calculate how the matter fields are excited by the conformal field theory, and use that to calculate Hawking radiation. And you get the right answer. You get the right temperature. You get the right gray body factors. Everything fits together very nicely. So at a minimum, this theory, which, remember, just came from saying that some of these diffeomorphisms at the boundary are now physical degrees of freedom, at a minimum, it gives a correct effective description of the microscopic states of the black hole in 2 + 1 dimensions. Perhaps it does more. If we really understood this conformal field theory, we might be able to show or tell whether it really fully describes the states of the black hole as a full quantum theory of gravity. We don't know enough about Liouville theory to be able to answer that. That's unfortunate. OK, so that was a summary of work that's a few years old. For the past few months, I have been looking at the application to asymptotically flat rather than asymptotically anti-de Sitter space. So let me say a couple of words about the reason for this. It would be nice to say, well, after all, this is our universe, but our universe is probably not asymptotically flat either. Probably we need to look at asymptotically de Sitter, and that's hard. On the other hand, locally, our universe is pretty nearly asymptotically flat. We can get far away from matter and get to a region that's very nearly flat. And over the past year or so, a group, I guess led by Andy Strominger, but including people like Stephen Hawking and Perry and a bunch of others, have been arguing that if we understood the implications of the symmetries of null infinity in asymptotically flat space-time, this might give us important new degrees of freedom that could account for black hole hair in some sense, that could lead to degenerate vacua, and might have something to do with the information loss problem in black hole physics. I'm not going to solve the information loss problem here, even in 2+1 dimensions. Well, in 2+1 dimensions, there aren't any black holes in asymptotically flat general relativity, so I certainly am not going to solve it. But I want to introduce some techniques that perhaps can be generalized to something more like our real universe, and which tell us something more about these symmetries ad infinity, the supertranslations and superrotations that Strominger and his friends have been so interested in. So here's a picture of asymptotically flat space-time, or that at least of the conformal compactification. One of the other advantages of working in 2+1 dimensions is that you can actually draw pictures that are reasonably accurate. So time slices are across here. This is null infinity, future null infinity, past null infinity. And I'm going to, as an analog to the Pfefferman-Graham coordinates that are used in the asymptotically anti-de Sitter case, I'm going to use what these days are called Bondi coordinates, though I'm told that this is not actually quite the coordinate system that Bondi first used. So here is the metric in Bondi coordinates. The basic things that go into this metric are that u is a retarded time. So the metric is foliated by these null cones of constant u, constant retarded time. And with this choice, in particular with this choice of the factor of -2, the radial direction r is an affine parameter along the geodesics that rule these outgoing cones. So you can think of the limit r going to infinity. You can think of that as taking a spatial limit, but you can instead think of it as following all of the geodesics along their affine parameter. And so you get to scry, to null infinity. There is a fairly trivial generalization of this, which is to stick in a more general function here. I don't think that that changes any of the conclusions that I'm going to reach, but I'm not sure. The one thing, I don't expect you to memorize this metric, but the one thing that I do want you to pay attention to is this factor of e to the 2 phi here. Oh, I should apologize. The traditional notation here uses a script phi as a conformal factor and a non-script phi as an angular coordinate. And I have not yet had a chance to go back and change my notation to one that makes more sense. I apologize on behalf of physicists everywhere. So anyway, the thing the one piece of this metric that's really going to matter is this script phi, the conformal factor here. This is just a measure of the failure of R to give the of 2 pi r to be the circumference of a circle. But in terms of the Penrose diagram, it's basically just the fact that you have the freedom to choose a conformal factor at infinity. OK, so the first step is to look at the behavior of that metric near infinity. That is, take that form, plug it into the Einstein field equation, see what you get out. The first thing you can do is look for symmetries that preserve that form. Those are the supertranslations and the superrotations. The supertranslations are basically just angular-dependent shifts along the null geodesics. The superrotations are just reparameterizations of the angular coordinate. And these are the symmetries that preserve that Bondi form of the metric. You can then stick the metric into the field equations. I don't have to because Barnish and Trossard have done that. And you can solve the field equations and find the formula for these remaining components, GUU and GU phi, in terms of the conformal factor phi. And you get something. It's just some expression. This is up to terms of order 1 over R. There are 2 arbitrary functions that depend on angle alone, capital theta and capital Xi. These have the interpretation of being the charges for supertranslations and superrotations. That is, that if you look at those transformations, you can just go through Noether's theorem and find the charges at infinity. And this is something typical of 2 plus 1 dimensions, that the source for a supertranslation is a rotation, and the source for a superrotation is a translation. OK, so we're interested in what happens to diffeomorphisms at a boundary. Yes?
I just had a question before you get to that. In 3 plus 1, what's the analog of superrotations? You don't hear about them in connection with the BMS group.
Right. So in 3 plus 1 dimensions, a superrotation is a meromorphic transformation of the 2-sphere at infinity. So there aren't any holomorphic transformations except for the ordinary rotations. If you allow poles, then you can generalize the BMS group to get additional superrotations. There is a debate as to whether these are really legitimate symmetries. There's an argument that that they can lower the Bondi mass arbitrarily and therefore should not count. In 2 plus 1 dimensions, they're perfectly well behaved. It's basically because diffeomorphisms of the circle are nicer than diffeomorphisms of the sphere.
But there's no genuine diffeomorphism of the sphere that corresponds.
Only if you allow poles.
Yeah, well, I wouldn't call that a diffeomorphism.
OK, yeah. Yeah, so, well, maybe if you say that your sphere at infinity has holes punched in it from, I mean, you could imagine saying that any physical null particle reaching infinity gives you a marked point, and then you might be able to do things that way. But yeah, I'm not going to especially argue in favor of those. Other questions? I should have said at the beginning, please feel free to interrupt with questions, which I probably won't know the answers to. This one I was lucky. OK, so we're interested in what the diffeomorphisms do at infinity. And to do that, we need to figure out first what the right boundary term is. If we were looking at spatial infinity, then we would know the answer. It's the standard given Hawking's boundary term. Well, that's if we're looking at spatial infinity and if our boundary conditions are that the behavior of the metric at spatial infinity is fixed in a particular way. Here we're looking at null infinity, so things are a little different. The straightforward thing to do is to just compute the boundary term. That is, look at the variation of the ordinary Einstein action, expand in powers of 1 over r. We're taking a limit as r goes to infinity, and see what boundary terms come from integration by parts and have to get canceled off. And what you find is that, well, first of all, you find some boundary term just by doing the calculation. You can then use the asymptotic expansion, play a few games with this, and what you find is that there is a total variation here, which is good. That means that's just an additional piece, boundary piece you can add to the action. And then there's a piece of the form e to the phi delta GUU. The tildes here mean that miraculously the terms of order r and order 1 over r all cancel out, and it's only the terms of order 1 that come into the variation. So what this tells you is that in order to have a well-defined variational principle at all, you have to either fix phi or fix GUU, which is that function of phi and its derivatives and the superrotation generator, or some combination. Yes?
When you talk about the boundary, like even from Gaussian spacetime, we know that it doesn't have a boundary, but when you compactify, it does.
Yeah.
So here, are you doing the action for the compactified version?
Yes.
But
well, what's the right way to say this? What I am doing is I'm looking at the action for the non-compactified version and taking the limit as r goes to infinity. You can then translate that into a statement about the compactified version by simply changing variables from r to 1 over r and doing a conformal transformation. But so I'm talking about scribe plus, in this case, in the usual way that it's defined, but without explicitly introducing the compactification. Other questions?
When you say that you necessarily have to fix those kinds of boundary conditions, how do you know there's not some kind of boundary term you could write down that gives you that?
Right. So in this case, you can actually tell it by inspection, because delta GUU has a term that involves, GUU has this arbitrary function theta that is completely arbitrary. And so there's no way of canceling off. So the variations of theta are independent of the variations of phi tilde, because theta is just an arbitrary function. So there is no term that will cancel there. I mean, more generally, what you do, you think of delta as being an exterior derivative on the space of fields. And so what you have here is a one form on the space of fields. And what you are asking is whether it's exact, whether it is a variation, a delta of some function on the space of fields. So you can actually analyze the cohomology of the space of fields, which I haven't done. But as a first step, you can just look at whether delta of this is 0, because d squared is 0. So if you have a one form omega that is d of something else, then d of that one form is 0. So you just look at delta of this, and you get something which is delta phi wedge delta GUU. And that's not 0 because delta phi and delta GUU are independent.
I think there might be more subtle than that, but keep on.
Yeah, I mean, it's not really much more subtle than that. I mean, it's a little bit more in the sense that you could have, well, no, actually it's not. You could have a more complicated cohomology in the space of fields, in which case you could have forms that were closed but not exact. But that would tell you that even if delta of this was 0, that wouldn't guarantee that it was delta of something. It's actually enough to just show that delta of this term is not identically 0 to tell you that there is no general boundary term that can cancel it off. This is typical, though. This is going to be true in any field theory, that if you look at the variation, say if you just think about the point particle, for instance, the variation of the action is going to have a boundary piece, which is p delta q. And what that tells you, first of all, delta of that is delta p wedge delta q. That's the symplectic form on the space, on the phase space of the point particle. And that tells you that you have to have as your boundary conditions fixing some function of p and q. Either p, the simplest choice is either p or q, or a linear combination. But you have to fix some combination so that delta p wedge delta q restricted to that, those boundary terms is 0.
I don't agree, but I wanted to see what else you have to say.
OK. OK, so you have a choice of what you want to fix at the boundary given this variation. I will choose to fix the conformal factor phi. That tells you what the boundary term is. You get a slightly different boundary term if you fix GUU, but not very different. So that's your boundary term. It doesn't look very geometrical. It's not something nice like the Gibbons-Hawking integral of the extrinsic curvature. As it turns out, though, it can be recast